I want to slow down and focus on something very specific inside our loop, and that is break. So this word gives us control from inside the loop. Basically, it tells Python, stop everything and exit immediately. But instead of keeping this inside this larger example, I'm going to isolate it so we can see it clearly. So I'm going to write a simple loop that counts, let's say, from 0 to 9, okay? Let's do that. For I in range of 0 through 9, sorry, through 10, okay? Because I'm counting from 0 to 9, which is 10 counts. Print I equal and the value of the I. So this loop is going to run 10 times. Let's run it and see what happened. So you can see here, it counts from 0 to 9. We don't want to run it normally, which is 10 times. Let's say we want to stop it early. I'm going to add a condition inside this loop. So the condition here will be like, for example, if I equal 5, then print stopping loop. And then after that, I'm going to use break. What's going to happen here is when I reaches 5, the loop should stop. Let's run it and see what will happen. Let me clear this. Notice what happened. The loop was supposed to go to 9, but the moment it hit 5, it exited the loop. That's what break does. It interrupts the loop immediately and stop it. In real systems, this is used for emergency stop, safety shutdown, invalid conditions, user interrupts. But sometimes we don't want to stop the loop. We just want to skip one cycle, and we can do that. So I'm going to write another example with another loop. Let's do that. So I'm going to write another loop, okay? For I in range of 10, here I want to skip one specific value, and that value that I want to skip is 5. So I'm going to put a condition that if I is equal to 5, print, just to kind of see the value, the index that we're skipping. So we'll say skipping, and then we'll just add the index that we are skipping, and then after that I'm going to say continue. So what I did here, I'm using a different word, which is continue. This means skip the rest of this cycle and go to the next one. Skip the 5 and go to the next one. Lastly here, I'm just going to say print, just to kind of see how it skips the 5 and goes to the next one. I'll just say give me the count of the index that are after the one that you skip. So let's run it and see what I mean by that. When I equals to 5, as you can see, is processing 0, 1, 2, 3, 4, skipping 5, and then goes to 6, 7, 8, and 9. So now we have two important tools. We have break, which helps us to stop the loop completely, and also we have continue, which helps us to skip one cycle and keeps going. In real systems, continue is used, let's say, when data is bad or incomplete or irrelevant. And instead of crashing, the system skips and keeps running. So now we can repeat, stop, and skip. But something deeper is happening inside every loop, and it has to do with how values change over time. I want to show you something subtle but extremely important. Inside every loop, there's always something changing, and that change is what gives the loop meaning. I'm going to start something simple. Remove this, okay? We'll do like battery level is equal to 100. This is our starting value, okay? Think of this as a battery percentage. I want the system to keep running while the battery is above 0. So how do we do that? While, again, battery level is greater than 0, as long as the battery has charge, I want you to keep running the loop. Inside the loop, I want to see the current battery level. Okay, well, let's print battery. I'll just put the value of the battery level, and then I'll just add like percentage like this. so that we can see it in percentage. Each time the loop runs is going to print the current value of the battery level. But just like before, we need change. If nothing changes, then there's no progress. So what we're going to do is here, battery level minus equal 10. This line reduces the battery by 10 each cycle. So every time the loop runs, the value moves forward. So let's run this and see the result. Okay, look what's happening here. Each cycle depends on the previous one. The loop is not restarting from the beginning, it's progressing. You can think of state as the current condition of the system and carried across time. The variable that we created, battery level, is outside the loop, but it is updated inside the loop. That means every cycle remembers what happened before. Now let's make it a little bit more realistic. This example is important because it kind of introduces something real systems need, which is state. And as I mentioned, state means the system remembers what condition it is currently in. For example, is the battery draining? Is it charging? Should the system keep running? Should it shut down? So let's write that step by step. So first, we have the battery level, and we created the battery level, and it's equal, we're going to keep that, which is equal 100. You can think of this, as I said, is the 100% battery level. And then we're going to add the charging equal false. So here, I'll just say charging equal false. We have this variable called charging. Right now, is false. That means the system is not charging yet. So we have two pieces of memory. Battery level tells us how much battery is left, and then charging, which tells us what mode the system is in. Then we start the while loop, which is while battery level is greater than 0, keeps running this loop. So as long as the battery still has energy, the system keeps operating. Inside the loop, we're going to print the current battery level as we did it before with the percentage. So this let us observe the system at every cycle, just like here. Next, we're going to remove this, okay? And we're going to add an if condition, and we're going to say if battery level is less or equal to 20, we consider it low. Next, we're going to do charging equal true. When the battery gets low, we change the system mode. We set charging to be true. It means what? This means the system is now in the charging mode. Let's print something while the system is in charging mode. We'll say print low battery charging mode activated. Next, we're going to add another condition. If charging, this line checks the charging state. Is it true? Is it false? In Python, if charging means if charging is true. Run the code below, which what we're going to add, battery level plus equal 5. Here, if the system is charging, we increase the battery level by 5. So the battery starts what? Starts recovering. Lastly, else, if the system is not charging, what do we do? Well, that's where else comes in. Battery level minus equal 10. If the system is not charging, then the battery drains by 10. So now we have two behaviors. If charging is true, battery goes up. If charging is false, battery goes down. Next, we're going to add if battery level greater or equal to 100. If the battery reaches 100 or more, that means it's fully charged. So what do? We don't need it to keep charging. Charging is false, so we turn the charging off by setting charging back to false. And this is how the system switches mode. One more if condition. If battery level less or equal to 0, finally, we add a safety condition. If the battery reaches completely zero or below, the system should stop. So we'll print here, system shutting down. We print the shutdown message. And right after the print, we add break. And break here exits the loop completely. This prevents the system from counting after the battery is dead. So let's run this and see the result. Now watch what happened. The battery starts at 100. Because charging is false, the battery drains. When it reaches 20, the system switches into charging mode. Then the battery starts going back. When it reaches 100, charging turns off again. So this loop is not just repeating, it is remembering its states, changing behavior, and switching modes. And that is the beginning of real system logic. At this moment, you've seen loops not just as a repetition, but as containers for evolving state. There's one final concept that makes this complete, and it has to do with how loops interact with collections of data. So far, our loops have worked with numbers and conditions, but in real programs, we rarely process just one value. We process collections of data. So let's create a list of sensor readings, like a temperature reading, for example. So we'll just call it sensor reading. Could be any sensor. And we'll create a list of values, 22, 25, 27, 30, 35, 28, and let's say 24. And now instead of counting with range as we did before, we're going to loop directly over the data. How do we do that? Well, for reading, now I can say for I, but I'm just going to call it reading just to make it more clear. In sensor data now, and I'm calling the list print, and we'll just say reading, and then we'll call the list of values. Okay, let's run it and see what happened. Notice the difference. We're not counting from 0 to 6. We're iterating directly over values. And this is how real systems process data streams. Not repeat 5 times, but process each measurement in that list. Let's add a logic to that. So for example, for reading in sensor reading, if reading is greater than 30, print, for example, high reading detected. And then I can just call that specific reading. Else, print normal reading. Normal reading. And then again, we call the value. Right, so let's run it and see what happened and see that behavior. Notice here, normal reading, you see all these, like they're starting with normal reading, 22, 25, 30, and when it reaches 30, here is saying is normal reading is 30. And then when it reaches 35, is it greater than 30? Yes, then this condition is going to be true, therefore is going to say high reading detected. And here is just, yep, high reading detected, and then it gives us the value, which is 35. Else, just basically normal reading. This is full pattern, loop, evaluate, and respond. And notice how clean this reads. For each reading, check condition, act accordingly. If this were connected to real hardware, the sensor reading list wouldn't be a list. It would be live data arriving over time. But the structure would be kind of identical. So let's add one more thing here. Let's call this average is equal to the sum of the sensor reading divided by the length of the sensor reading. We'll print average temperature, assuming that this is a list for temperature readings, and then we'll call the average. Let's run this and see what happened. You can see here, average temperature at 27.2857 and some decimals. So now we're not just reacting to individual values, we're analyzing the data set as a whole. And this is how systems are moving from reactive behavior to informed behavior. And now you've seen loops in every major form. fixed iteration, condition-based repetition, infinite runtime loops, state evolution, and data processing, as we saw here in finding the average value or the average temperature of these readings. Let's take a step back for a moment. What did we actually build today? We started with repetition, then we added conditions, then we added state, and lastly, we added data. But underneath all of that, there's one pattern, and that pattern is this. While true, read the input. Okay? Just remember this pattern. Evaluate, conditions, update, state, and lastly, act. This is the universal runtime pattern. You have read input, could be sensors, user commands, network packets. Then evaluate conditions. Is something too high, too low, invalid? Then update the state, which is, let's say, change internal variables. And lastly, act, which is respond. This structure exists inside drones, cars, medical monitors, AI systems, even operating systems. When people say programming is about syntax, they're missing the point. Programming is about structure, and loops are the structure that keeps system alive. When you write for reading in sensor like this, in sensor readings, okay? Or when you say while temperature is less than 40, you're not just repeating the code, you're defining how a system behaves over time. Time is what makes systems real. Without loops, your program runs once and dies. With loops, it persists. And persistence is the beginning of intelligence. So now you understand something most beginners don't. Loops are not about printing numbers. They're about sustaining behavior. Today, we didn't just learn for and while loops. We built something more fundamental. We built rhythm. When a system repeats, it observes change, and that change in itself, it can respond. And when it can respond, it can stabilize. And that stabilization is what keeps drones in the air, what keeps power grids balanced, what keeps processors alive. And here you can see it clearly. A loop is not just repetition, it's controlled persistence. If statements taught our code how to decide, loops taught us today how to sustain. But there is something missing. We can repeat, we can decide, we can manage state, but our code is still flat. If we want to build real systems, we need structure. We need reusable pieces. And that's where functions comes in. We can build what we just did today, but inside functions. We'll take these in the next episode, and we'll take these loops and start turning behavior into modules, because intelligent systems aren't written in one block. They're built in layers.